Okay, good evening. Today's lectures, we will go through another topic, is the sound publications and sound effects. Okay. In this topic, it is relevant to your lab sessions in the next week, so that please pay more attention on that. But it is not so difficult. We just make use of the simple and fundamental knowledge of sound acoustic effects. We are able to understand what we are doing in this lecture. Okay. In this lecture, we will go through according to the teaching plan. We will finish these lectures tonight. Okay. I mean that you can download this PowerPoint from the Blackboard. Okay. In the last time, in the first two lectures, we just considered that I told you that we can consider acoustic source. This is a simple point source. Okay. We make it as a port, very small ports, and you can radiate sound fields in all directions. Okay. This is the first concept I want to share with you in the last two lectures. Okay, make sure this one. Actually, the publications of sounds we can derive into outdoors and indoor publications. Okay, you know that for example, the road traffic noise or railway traffic noise, we can regard this as the outdoor publications effects. Within this room, when I'm talking with you now, we may consider that this is an indoor publications. When we consider an indoor environment, we need to consider both two components. The first component is the direct field. Okay, the direct field is that when I'm talking with you, the direct effects, the sound fields generated and publicates to you. This is the first component, and the second component is from the surrounding environments due to the reverberations effects. Okay, sometimes it is rather difficult to control reverberations effects because it is relevant to the geometries and configurations of this room surfaces, because you know that not all room surfaces they are regular in pattern. Okay, some of them they are irregular pattern, so that's why we need to think about that, how to make sure that we can achieve good indoor environments. Okay, starting this lecture, we will go for outdoor sound applications first. When we consider the type of source, noise source, in the previous two lectures, I always emphasize that we just need to consider that this is a point source. Now, in this lecture, I want to share with you that, for example, if we have an array of loudspeakers, or if we have a stream size of traffic flow, okay, or railway, okay, railways with we have different vehicles connected together, we cannot just simply consider that this is a point source. We will consider that this is a live source. Okay, more complicated. You may consider that live source is consisted of multiple point sources together. And the sound propagations effects in outdoor environments, it could be affected by distance. The longer the distance, the lower the sound intensity effects or sound pressures. And we still need to consider that whether there are any obstacles such as the reflective barriers or any surroundings environments. So we still need to consider the directivity factor. I'll explain to you that how to assess this one. And some of them are minor factors such as the atmospheric absorptions, temperature, wind, and humidity. In the first lectures, I told you that when we consider that there are two layers of temperatures, the upper layer, because the temperature is higher than the lower layer, so that's why you may make the applications of sound effects into bending effects. Okay, this is the reflections effects. Okay, for the first few pages, we will go through how to consider an acoustic source. This is a simple one. A point source, you can radiate sound fields in all directions. And because this is similar to a sphere, so we call this one is the spherical wave, okay? And we call this one is the monopole sound source, okay? Just have a single source. So that's why we consider that this is the monopole source. And the sound pressure levels could be decreased by 6 dB when we double the distance. I explained this one before in the first lecture, so you may refer back to the relevant context. The second one, in the first tutorial, I introduced a term to you is the pin wave. Okay, for calculations simplicity, sometimes we need to consider the scenarios that this is a pin wave. For the pin wave, it means that all the wavefronts they are parallel to each other. Okay, but if you consider that this is a point source, this is a spherical wave, we are rather difficult to achieve this one. If we use a plate generator like this one, a vibrating plate, we can generate more likely a pin wave like this one. But we don't have, in reality, we don't have perfectly spherical wave or perfectly plane wave. Okay, we can only achieve an acoustic source in between these two scenarios. We do not have a perfect situations. We can so that in this slide, I just want to show you that we can generate a plane wave using a large radiator. And the other one is the piston source. This piston source is more likely to be more realistic. It is in between a simple spherical wave and plane wave generator. This model that can give a closer approximation to the acoustic behavior of real sources. When we refer to this diagram, okay, you can see that what is A? A is the radius of this piston source, is the dimension, and K is wave number. Okay, why Ka is approximately equals to 1? I call this one is low frequency. If you forget about what's the meaning of wave number, you may refer to this page. When you refer to the supplementary information here, there is a term here, wave number. It is relevant to wavelength. Okay, so that what's the relationship between them? This is a reciprocal relationships. The largest the wavelength, the highest, the smaller the wave number. When the wave number is smaller, what does it mean? It means that the frequency is lower. Okay, you can see this one. We just use a very simple relationship like this. Because K is relevant to lambda, if we increase the wavelength, the values of K could be decreased, correct? When you refer to this one, 2 pi is a constant value. We cannot make any change. Okay, because we have this simple equation, C is equals to F lambda. If we increase the wavelength, it means that the frequency is at low level. Okay, so that's why reference to this simple relationship, K is relevant to frequency. Okay, when you go back to this one, A is a constant value. It depends on the geometries of this radiator. When it is approximately equal to 1, it means that K is at low level. When K is at low value, so it is under low frequency. The shape is like this. It's similar to a spherical wave. When we increase the frequency at high frequency, that means we increase the wave number, so that it becomes like this. This is similar to a plane wave. So that's why some people call this one piston source is more closer to our realistic source. It is in between the spherical wave and the plane wave. Okay. And the dipole source, just we have two multiple sources. Okay, when they are working together, it could create the super interference effects. Some of them could achieve constructive interference, and some points could achieve the destructive interference. So that you can hear the louder or softer effects when we operate these two effects together. Okay, this is an animation to show that when we have a dipole source under the effects of the principle of superposition, or you can call this is the interference effects, you can achieve the pattern like this. Okay, now let's go back to the point source. Okay, for the point source, I already explained to you that the source power is equal to IA. Okay, this is a very fundamental definition for what is sound, what is acoustic power, what is acoustic intensity. A here, if we consider that this is a point source, as this is a spherical wave, so that's why the surface area is equal to 4 pi r squared. Okay, no any you know this one before. Okay, I explained this one to you. If we you may ask the questions to me that under what situations we need to consider that this is a point source, and under what scenarios we need to consider that this is a live source. It depends on real situations. Okay, if we just consider that we have a single loudspeaker, we can simply consider that this is a point source. If we have an array of loudspeakers, okay, you cannot consider that this is a single source. Okay, so that's why we may consider that this is a live source. In this one, we just go back to the fundamental principle. Is these two equations? Okay, now in the first lectures, I explained this one to you. Okay, even in the first tutorial, I explained this one to you. Actually, these two equations, they are exactly the same. Okay, just we want to we encounter different situations, we may use different parameters for our calculations. Now, as I explained before, as I emphasized before, we just use some pressure level and some power level for our calculations. We seldom make use of the some pressures or some power for our calculations. So that's why we want to have an equations that can help us calculate directly, rather than we need to do calculations repeat and repeat again, even in your final exam. This is the equations. This is the equations. These equations, when you refer to this one, SPL, it refers to some pressure level. SWL is some power level. R is the direct distance between the source and the receiver. And this is a constant term. Okay, when you refer to this one, on the left-hand side is some pressure level. The reference value is this one. Some power level. The reference level is this one. How we can achieve this one? You do not need to derive anything about like this. Okay, this is just to help you understand why we can achieve the final results. From the beginning, from the first principle, we have these equations. We rearrange the first equations to this form, and then we make the right-hand side and the left-hand side, they are equal to each other. You can see that we put the reference values for some pressures on the left-hand side and right-hand side together. Why we need to do that? Because we want to construct the standard equations for some pressure level and some power level. Okay, so that we can arrive at simple equations for helping us to calculate our results. When you refer to this one, you can see that we also incorporate these two reference values on the right-hand side. Okay, when you cross out all the terms here, you can go back to this one. Okay, this equation is the same as this one. Okay, we just want to construct the relationship, and then you can follow the steps here. On the left-hand side, we take 10 knots on both sides. You can see that this is exactly the standard equations for some pressure level, and this one is for some power level. To split these two three components into different form, this is just a simple mathematical presentations. Okay, when you refer to this one, why I say this is equals to 0? Because when you substitute the reference level for power, pressure, the densities of air, and the speed of sound into this term, it is about equals to 0. When you refer to some reference books, they also cater for this points. This term, okay, is about 0.3 something. Okay, very small. You can ignore this term in our study, so that when you ignore the second term in these equations, we just have the first one and the last one and write it into this one. Okay, you can see that this one we can also write it into these two terms. Okay, you can see this one we can split into this one and this one. Okay, do you still remember that if we have a simple relationship like this, lot A, B, we can write it as lot A plus lot B? Okay, so that's why we can further rewrite it into this form. Okay, now when we go to this one, we can just simplify it as some pressure level is equal to some power level minus 11 minus this term. This term is relevant to the distance. The longer the distance, the lower the some pressure level. Okay, it obeys the physics law in this one. Okay, this equation is specifically for a point source only, for a point source. So actually, you only need to consider and memorize these equations only. Okay, you do not need to these formulations. They are used to help you understand why we can achieve the final results. At the beginning of in this one, when we consider that this is a point source, there is a statement here to state that the some pressure level it could be decreased by 6 dB when we double the distance. You can check it by yourself using this equation. This one. Some power level, it depends on acoustic source. It could not be changed when we increase the distance. So that when you change the values R, double the values of R, the some pressure level could be decreased by 6 dB. Okay, let's say if you substitute R is equal to 5 meters to get one value, and then you substitute 10 meters, you can get another value. The first value and the second value, the difference is 6 dB. Okay, some power level, remember, it is the same. Okay, so that there is a statement here. If we consider that this is a spherical wave applications, given some pressure level will decrease by 6 dB when we double the distance from between source and receiver, and we call this one is the inverse square law. Okay, inverse square law. So this is a figure to show the linear relationship using these equations. When we double the distance, it could be decreased by 6 dB. The second one is live source. For example, in this case, we have a number of loudspeakers. They are aligned on a straight line. In this case, we cannot just simply consider that this is point source. We can consider that this is a live source. Okay, reference to the term here, you may imagine that this is a straight line. When you consider this one, how we can find out the resultant equations to show the relationship between the some pressure level and some power level? We start from the same principle using this one. W is equal to IA. W is some power. I is intensity. A is the area. But in this case, when we consider that this is a live source, now the surface area is not equal to 4 pi r squared, because you can imagine that when all these loudspeakers they are operating together, this is similar to a cylindrical. Okay, so we call this one is a cylindrical wave. It is similar to a cylinder. In this case, we derive another equations. I skip the formulations here. You can just plug in the area is equal to 2 pi RL. 2 pi RL. 2 pi RL is the surface area or the cylinder. Okay, so that's when you just replace 2 pi RL for the area here. Okay, when you replace the term 4 pi r squared by using 2 pi RL into the same equations, follow the same principle. what we can achieve? We can achieve this one, this equation. Okay, this equation is different from the previous equations, mentions the effects of spherical wave. This is used for live source. Okay, reference to this equation, R is the direct distance between the source and the receiver, and L is the length of this live source. Okay, the length. But when we just consider these equations, you can see that when we double the distance, the change is just 3 dB instead of 6 dB. Okay, if we keep L as a constant value, you will keep it as a constant value. When we double the source and the receiver, the distance, I mean the separation distance, the change is just 3 dB reduction. Okay, this is the second equation. This equation is used to represent the effects of live source to identify the propagation effects from to construct the relationship between the some power source and also the sound pressure level. Okay, now this one is just considered the effects of direct field without encountering any obstacles or without the presence of any reflection effects. Now, if we consider this as an indoor environment, an enclosed area like this inside this room, okay, we cannot just consider the direct field. We still need to consider the reverberation fields because some sound fields hit on the physical boundary like this one, okay, the walls, the ceilings, and also the floor, okay, reflections could occur. So that's there are two major components. The first one is sound direct field, and the second one is the reverberation field. Some people they define some terms free field. It means that without sound fields, without encountering any obstacles, we call this is free field region. Okay, this is free field. When you compare the upper figure and the lower figure here, you can see that this is the source. When the region is very close to this acoustic source, we call this is the near field. Within this near field region, it could not follow the inverse square law. When we double the distance, it could be decreased by 6 dB. But in the free field region, this one, without encountering any obstructions, it could follow the inverse square law. And the far field regions, what is far field? It begins where the near field ends and extends to infinitive. This is the far field regions from the regions of near field to infinitive. Direct field, reference to the term, it is very simple. Without any obstacles, we call these sound fields. They are direct fields. Reverberation fields, if we first that part of the sound fields reflected from the physical boundaries, or then we can classify they are reverberation fields. So that, simply speaking, we just need to consider direct field and reverberation field inside and indoor environments. Okay, now, in terms of the directivity factor, why we need to consider this one? Okay, let us look at the definitions first. Directivity factor, it is defined as the ratio of the sound intensity in a given directions measured at a center distance from the source divided by the average sound intensity at the same distance. So that when you refer to statements here, it is not so clear. So please consider the equations here. This is the definitions, is the ratio compare the intensity at any points to the intensity, the average intensity. Okay, this is the ratio. Some people also proposed the directivity factor. The directivity factor is relevant to this one. They just write it as 10 not Q. When we apply the logarithm functions, the units, they are always equal to dB. Okay, please pay attention to this one. Okay, what is the difference? We just consider that directivity factor is just a figure. It's just a figure. And DI directivity index, it is expressed in terms of dB. Okay, now let me please go to this one. When you add law the values Q here, I introduced these equations to you before, correct? This one. Okay, before that, I introduced these equations to you. Okay, now we plug in one more parameter here, is what we call the directivity factor, to see what is the difference. If we consider that, when we take a look on this figure, if we consider that this is an acoustic source, it is suspended in the middle, inside the room. Okay, you can radiate some fields in all directions, correct? What is the surface of this equation? What is the surface area? 4 pi r square, correct? Okay, when this source is suspended in the middle of the room, the surface area is 4 pi r square. When you compare this one and this equation, Q must be equal to 1, correct? Otherwise, they are not equal to each other, correct? When you compare this equation and this equation, Q must be equal to 1. Okay, so this is the first case. For the second case, when we put an acoustic source on the floor, you can radiate sound fields in a hemisphere area. Okay, like this, you can see that the surface area it becomes. For the second case, the surface area it becomes 2 pi r square because the surface area is generated from this hemisphere. Correct? When you compare this equation and this equations, when you make it equalize to each other, Q must be equal to 2. Okay, so in the second case, the directivity factor must be equal to 2. Okay, now, when we put an acoustic source near the wall, okay, any one of them, okay, inside the room, the surface area in this case, it becomes pi r square. In this case, Q must be equal to 4. And the last one, when we put it near the corner, Q must be equal to 8. Okay, so that we have 4 simple cases in the middle of the room, center positions on the floor, near the wall, and at the corner. Okay. Okay, in your final exam, okay, you have to read carefully about the descriptions. I could not tell you about the values of K. You need to consider that whether the Q is equal to 1, 2, 4, or 8, depending on the descriptions. Let's say when I tell you that it is near a wall, okay, one of the walls, you can just find that Q is equal to 4 by yourself. Okay. In the first 2 lectures, we just focus on this one, the first case. We assume all the point sources you can radiate some fields in all directions. So that Q, we just write it as 1. Okay. This is just for simple cases. Q can be any values, not just an integer. Okay, not just an integer. Q must be any values. Okay, now when we can determine the values of Q, when we determine the values of Q here, the directivity factor is equal to this one. When Q is equal to 1, substitute into these equations, the corresponding directivity index is equal to 0. Okay, when Q is equal to 2, it becomes 3 dB. When it is equal to 4, it becomes 6 dB. Okay, just depending on this equation. Okay, what does it mean? Okay, let's say the values of Q is equal to 2. In the second case, Q is equal to 2. It means that the sound intensity in a certain directions, when it compares with the average one, is double. the intensity is double higher than that or the FH1. Okay, it is correct because when you look at this case, okay, based on the conservations of energy, you can only weigh these samples in this directions only. Okay, when we compare with the FH intensity, it should be double the overall the FH1. Okay, so that this is the definition. But please bear in mind that Q is not always equals to positive integer. Okay. Okay, let's say in this one, I derived these two equations to you before in the previous slides. If we need to consider that the directivity factors, we also consider this one cannot Q. Okay, we just incorporate one more parameters into these equations. When you consider this one, no matter this is a point source or live source, both of them we can consider that Q is equal to 2. The reason is that all the acoustic sources they are located on the floor. Okay, so even we just have a car, single car, we simply consider that this is a point source, Q is equal to 2. Even we have a traffic flow like this, we classify this as a live source, Q is still equal to 2 in this case. Okay. When we consider that Q is equal to 1, okay, when Q is equal to 1, what happens? Okay, when Q is equal to 1, it means that this term is equal to 0. Okay, so you can consider, you can compare these equations. Why? In this term, we do not need to consider the directivity factor because in this case, we consider that Q is equal to 1. Okay, and finally, when Q is equal to 1, the directivity index is equal to 0. So that we do not have the directivity term here. But in your calculations, you must consider the directivity effects. Okay, it depends on the locations. Okay, now, in terms of the indoor sample applications, we have two components. We just need to consider two components. One is direct field, and the other one is the reverberations field. When you consider the effects like this, you can see that reverberations components is similar to a background noise level. Okay, background noise level. But for the direct field, when we increase the distance, it could be decreased like this. Okay, so that's when you add them together, the direct field and the reverberations fields together, we can achieve the total effects. Okay, but the reverberations effect it depends on the surroundings areas or indoor areas. Okay. In the second lecture, I introduced to use that these terms, the room modes. I also let you know how to calculate the standard wave. Okay. At that time, I just introduced the basic concept about we have 3 different cases: open tube, open closed tube, and fully closed tube. Okay, 3 different cases. Now, why we need to study this one? Because we can apply this one to study the effect of room modes that can occur inside any indoor areas if we do not have a better indoor acoustic design. Okay. What is room modes? Room modes are actually the resonance effects that exist in a room when the room is excited by an acoustic source such as a loudspeaker. In these subjects, you may encounter this term many times: resonance. Resonance, you know that you could amplify the effects. Okay, how to we can observe resonance in many areas, no matter we study the sound effects or vibrations effects. Let me show you a simple demonstration. Okay, in this video you can see that this gentleman he uses two tuning forks. One is 550 hertz, and the other one on the right hand side is 440 hertz. To make it into motions, let us see what happened. When these two instruments they are not at the same effects, same acoustic effects, there is no any change. Now we choose another one. This is resonance effects. Okay. Okay, what is the principle of this one? Because both of this one, they are under the same acoustic frequencies. So that's the frequency effect, the acoustic wave effects excites the vibrations of this tuning fork. When the tuning fork is into vibration, so that it can make the adjacent board into motion. This is resonance effects. Okay, so that's we consider that room modes are resonance effects. How to calculate this one? This is an animation I demonstrated to you before. We make use of these equations. These equations are actually just very simple. When we consider this is a rectangular room, okay, this is the rectangular rooms with their corresponding dimensions, the width, the length, and the height. Okay, you can see that M and O. We call this is the mole numbers, the corresponding mole numbers. Only positive integers only. Okay, for M and O. And L, W, and H, it depends on the real configurations and dimensions of for the room. Okay, when you compare these equations, you can find it in our previous lecture. Okay, when you take a look on this one, we can consider that this is a fully closed tube, correct? When you consider this room is a tube, you can compare. My lecture looks here. Okay, in the previous lectures, I introduced to you that we have 3 different cases. For fully closed tube, we use the same equations. Okay, as the same as the open tube. Okay, please compare this equation. F is equal to m. V is the speed of sound derived by 2L. This equation is equal to this one when you just consider one dimension only. Okay, if you take out this one and this one. Okay, can you observe this one? When you set N and O, they are equal to 0. Just consider M and L in this case. This equation is the same as the fully closed tube. The equations for the closed tube. But now we just need to consider that the 3 dimensionals, the length, the width, and the heights of the room. So we have these equations. Okay. Okay, how to consider this one? If we just there are 3 different modes. The first one is the SL mode. SL mode is the easier one to trigger the SL mode because we just consider 2 parallel surfaces. When you consider this one, it could only happen when we set the other tools, they are zeros. Like this one, when we set M and O is 1, 0, 0. What does it mean? It means that we do not consider this one and this one. We just consider the values of M. Okay, SL mode, it means that we just consider it happens in 2 parallel phases. The second one is the tangential modes. Tangential modes, it could happen when any 4 parallel surfaces, they could generate the reflection effects. At that time, we need to set any 2 of them, they are non-zero. They are non-zeros. Okay, for the tangential mode. In this case, let's say M and O, you can set 110, 011, or 012. Okay. We can only set the parameters M, N, and O as positive integers. Okay, you may ask why we can set it is equal to 2, 3, 4, 5. It means that we can achieve the higher frequency. If the effects it involves 6 services, we call this one is the obvious modes. In this case, M and O must not be 0. Okay, must not be 0. Okay, let's say when we consider the SO mode 100 that can be generated inside a room, the room dimensions are 5 meters times 4 meters times 3 meters. The fundamental frequency is this one. When you refer to this equation, we set M is equal to 1, N and O they are 0. So that's under 34.3 hertz. This is the first mode. This is the first mode to achieve this one. Okay, let me show you an example video here. We stop here. For this one, I just want to show you that we have, in total, we have three types of room modes. Okay, the first one is the SO mode, the second one is tangential, and the last one is orbit mode. When you compare these 3 types of modes, it is easier to generate for the SO mode, okay, because we just need to 2 parallel services. We can create an SO mode. But if you consider orbit mode, it should involve a total number of 6 services. That means involve all the services inside this room, okay? It is harder to achieve this one. And under multiple reflections, the effects could be decreased significantly. So that when you compare one by one, when you compare the first 2, tangential modes could be decreased by 3 dB when we compare to the SO mode. And the orbit mode, it could be decreased another 3 dB when we compare to the tangential mode, okay? This is the first one. So when I ask you to find out the SO mode, you can just plug in the values. One of them, no matter this is M and O, one of the parameters, it should not be equal to 0. Other 2 must be equal to 0. This is the SO mode. Okay, for the second one is that 2 of them should not be equal to 0. And the last one is that all the parameters, they must not equal to 0. Okay, let me show you another one. You can find any online calculators. Okay, you just Google it. This time room modes calculators. You can search many online calculators. For this one, let's say this is one of the online calculators. In this one, you can set the length of this room is 5.2 meters, width 4 meters, and height is let's say we change it to 3 meters. Okay, so when you look at this one, NS, NY, and NZ, they correspond to the parameters M, N, and O. Okay, so that's what is the meaning of NS is equal to 1. The first one is the SO mode. The first one is SO mode because we just consider that one of the parameters it is not equal to 0. Other 2 are equal to 0. Under the dimensions here, you can check by yourself by using the equations stated in your lecture notes. The first frequency it could achieve resonance effect is at 33 hertz. The effect is like this. How to read the figures here? This is x-axis, this is y-axis, and the height is the z-axis. Okay, when you refer to this one, the dark regions represent higher sound pressures could be resulted. Okay, please remember that room modes is not a good interior effect. We don't want to have it because you could make some regions inside a room with higher sound pressures and some regions with lower sound pressures. This is not we want to achieve. Okay, so that's why we need to install some absorptive material inside the room in such a way that we can avoid the presence of room modes inside interior areas. Okay. So when you select another one, the second one is that when we set n is equal to 1, other 2 parameters are 0. Okay, the situations it becomes like this. Okay, still remember that when we go back to the first one. When you go to this one, when you consider that this is a single tube, okay, on this side and this side with higher sound pressures, correct? When you compare the simulations like this is the when we consider a tube, standing wave, it forms inside this tube. The variations, the fundamental mode is like this. On both sides, the sound pressures, they are under higher pressures compared with other regions. Similar to this case, okay, when you consider the tube like this. On this side and this side, they are under high pressure. In the middle of the room, it is under lower pressure. Okay, can you observe this one? Can you compare the figure here and the animations here? Okay, when we go to this one, what is this one? This is the tangential mode. Because M and N, they are not equal to 0. Okay, we set they are equal to 1. Okay, this is tangential modes. Reference to these animations, the dark regions under higher sound pressures, and the lighter regions, they are under lower regions. To match the acoustic effects, they are not uniformly distributed inside rooms. Okay, this is not the targets we want to achieve. Okay, for this one, for these calculations, they are referring to this equation. Okay, but please pay attention. The units for the frequency is in terms of hertz, C is the speed of sound, and M and O, they must be equals to positive integers only. Okay, any problems about how to calculate room modes? Okay, this is not this is an adverse effect when we encounter room modes. Some of the general acoustic designs we can ignore this effect, or we can get rid of this effect. Is the first one is to avoid rectangular rooms with dimensions relatively to by simple ratio. Okay, in the past, many students just when I asked these questions in front of them, they just told me that to avoid the design of rectangular rooms, this is totally incorrect. Okay, you can see that inside this room, this is a rectangular room. We can design a rectangular room, but with they are not related to using the simple ratios. Okay. And the second one, we cannot change this one, okay, because the design of the dimensions, it depends on the situations decided by an architect, not engineer. We cannot to achieve this one. We can install some absorption materials, okay. Let's say inside this room, although we do not install absorption materials on the wall surfaces, but the carpets, it is absorptive material, okay, and even the ceiling, it is absorptive material, okay. And the third one is to make opposite surfaces slightly long parallel, okay. When we cannot generate reflective wave and they could not superimpose to each other, it means that standing wave cannot be formed. If there is no standing wave, it means that there is no room modes. Okay, sound absorptions and sound proven. In the past, many people make confused about these two terms. Sound absorptions, it refers that the loss of energies when sound waves hit ceilings, walls, and floor, and they can be absorbed. The sound effects can be absorbed. We use sound absorption materials to absorb the reverberations effects. And sound proven, another term is sound broken. What does it mean? It means that we do not allow the passage of sound wave from one area to another one. It means that, for example, we are in lecturing class now. Okay, the provisions on the wall here is to prevent the sound effects from this room to the adjacent one. Okay, this is what we call the sound proven or sound broken. For the sound absorption effects, we have a parameter. A classical parameter is sound coefficients, sound absorption coefficients. There is no units. The range is from 0 to 1. We use the range from 0 to 1 to identify the absorption performance of the material. For example, if this is a hard wall, when we have an incident wave, most of the sound wave could be reflected. Only little portions could pass through these hard surfaces. Okay, so that's the heavy structure here. Alpha is the coefficients. It's equal to 0.05. When it is closest to 0, it means that it is highly reflective. When we install a material, absorptive materials, okay, attached on this heavy structure, and this one, most of the energies could be absorbed. Only a few portions of energies could be reflected. At that time, the absorption coefficients of these materials is far away from 0. It's not equal to 0. It's closer to 1. So we use this parameter to define the effects of the absorptive materials. Okay, when it is equal to 1, it means that this is highly absorptive material. If it is closer to 0, it is highly reflective material. Okay. And the definition is that this is the ratio WA and WI. This is the energy, sound energy absorbed by material to the sound energy that can be absorbed by perfect absorber. Okay, if we have a case like this, if we have an openable window, let's say this is openable window. When we open the window, this one, what is the sound absorption coefficient of this openable window? It is equal to 1. Okay, because all sound fields can pass this openness to outside. Okay, this is a perfect absorber. So because we need to calculate different materials, they have different absorption coefficients. Okay, when you compare the wall and also the carpets, the absorption coefficients, they are different. So that we need to calculate using the basic equations like this. What is S? SI is the surface area. If we just consider that this is a single room, if we just consider this as a room like this, a rectangular room. Okay, we have a total number of 6 surfaces. Okay, 4 walls, the top ceiling, and also the floor. Okay, so that we have S1 to S6, and because the materials they can be made of different materials, so that it has the correspondence value. And when you use this term SI times alpha I, we call this one is A. What is A? A is what we call the room absorptions. The units is meter square supreme. Reference to this one, please pay attention. This is not the geometrical area. This is the absorptions effects, meter square supreme. When you refer to some reference books, they could just write it as meter square. Okay. I repeat again. This one is the geometry, is the geometric dimensions. Okay. The units is meter square. Let's say the ceiling area is something meter squares. Okay. And how about alpha? Alpha, the range should be equal to 0 to 1 only, and there is no units. This one, we call this one A. A is the room absorptions, the total room absorptions. The units is meter square supreme. And some reference books, they could just write it as meter square. But this meter square is not the geometric area. Okay. Any problem? So we have this one. When we want to find out the total absorption coefficient, is A is equal to SI times alpha I. Okay. How to find out the FH values? Let's say we have a total number of 6 surfaces inside this room. If we want to find out the FH values of each surface, when you get the result, total area, this is the total absorptions derived by the total surface area. You can find out the FH value. Okay. Okay, let's take a look on this one and we take a break. When you refer to this one, we need to do the frequency analysis. Reference to this figure, you can see that different materials, they have different absorption coefficients. The coefficients must be in the range from 0 to 1. When it is equal to 0 or near to 0, it means that it is highly reflective. When it is closer to 1, it means that this is highly absorptive. So you can compare that concrete block at low frequency, the result is 0.36. But please pay attention, you can see the water surface. Water surface is just 0.008. It means that the absorptive reflection effect of water is much higher than that for concrete. Okay? When you compare concrete block and also water, water is highly reflective when you compare these two materials only. Different frequencies, they have different performance. Okay, and this is a figure I extracted from some reference. You can see that the variations of absorptions effects across the frequency value. Okay, let's take a 5 minutes break. If you have any problems about the first part, you may ask me. Okay, another one. Before you go to toilet, let me talk about this one. I already sent you emails about the lab sessions arrangement on this 5 day. Okay, please take a look on the. We need to divide into 2 groups because our Lois lab cannot cater for all students at the same time. We divide into 2 groups. You have to refer to the assigned group leads to attend the tutorial class here and also the noise lab in our block set. Okay, and although we have 2 groups, the arrangement, the teaching material, all of them are the same. You can form your group mates amongst 2 different groups. Okay. Okay, let's come back. Remember that these 2 lab sessions are compulsory. This is not my requirements. This is the department's requirement. So that please arrive on time because our schedules are so tight. And in addition to these lab sessions, we still have 2 tutorial sessions on the next 5 days in this room. Okay. So that I cannot take in charge for both spaces. I could be there in the noise lab to teach you how to do the experiments. So that my teaching assistants will take in charge in this room to teach you the tutorial sessions. Okay, now let's go to this part. There's some in this slide we have some common building materials to show the effects, the acoustic effects. I just want to pick up one thing to you is this one, glass. Glass is a mixture of silicates. This is normally it is reflective in high frequencies, but absorptive at low frequency. What does it mean? It could be resonance. When we have a double layers, okay, this is a common practice where we install double layer panels to reduce the noise level. Okay, we need to select the criteria, the criterions that you could not achieve the resonance effects. Because if we have a double layers arrangements under the resonance effects, sometimes under some certain frequencies, the noise effects could be louder than when we use a single layer. Okay, this is the tricky points. Similar to this one, you may imagine that You may imagine in this simple experiment, if we have two layers, okay, one by one, under the resonance effects, both of them could be operating into vibrations, so that you could generate a louder sound effects. Even we use double layers. Okay, now I introduced this to you before in the first half. A is the total absorptions. When you reverse this one, A is the room absorptions. How to calculate A? If we consider this is a rectangular room, you have to sum up all the surfaces. With each surface, we have their corresponding absorption coefficients. Okay, and how to calculate the average absorption coefficients? The average one, alpha m, this is the average one, is equals to A, the total absorptions derived by all surfaces. So we know how to calculate the values A and alpha m. Some people also proposed another parameter. We call this one is the room constant. Room constant is A divided by 1 minus alpha m. No matter RC or A, the units is right. We can express it in terms of meter square spleen. And some reference books, they just skip or simply write it as meter square. Okay, we can make use of this one to estimate the effects of reverberations on the noise level within an enclosed area. What is the meaning of the last statements? When RC becomes smaller and absorption coefficients unchanged, the room becomes more highly reverberates. What does it mean? If we keep this values constant, okay, we do not change this one. If we decrease the values RC, what happens? The results on A could be decreased, correct? If the amount of absorptions is decreased, it means that the reverberations could be more pronounced, it's more obvious. Okay. If we decrease the use of the absorptive materials inside a room, it means that reverberations effects becomes more obvious. Okay. So this is the last statement. You may challenge that for the last statements. If we decrease the values of A, actually we also affect the values of alpha m. Okay. But here I just want to keep one of the parameters is a constant value. For this one, sound pressure level within a room. I told you before, when we consider the effects of a room acoustic effects, we need to cater for two parameters, direct field and reverberation field, correct? So that it could generate the total sound pressures. How to calculate, why we can state this one. On the right-hand side, PD refers to the direct field, the sound pressures for direct field, and PR it refers to sound pressures for reverberation field. Why we can construct this one? Do you still remember that we have this one. If we consider just two sources, now we have two components, direct field and reverberation field. When we consider the first part here, we can construct this equation, correct? Okay, now so that's why we can write the total pressure square is equals to the direct field pressure square plus the reverberations one square. Okay, I could skip the how to derive this one. Let us go to this equation. Let me explain this equation first. In the first half, I show you that if we want to construct a simple relationship between sound pressure and sound power level, we have an equations for point source and light source, correct? Now we can write it into this form if we cater for the direct field and the reverberation field. In this equation, this one is the sound pressure level, okay? And this one is the sound power level. How about this one? This one is for direct field. And this one is for reverberation field. Okay? What is Q here? Q is the directivity factor. It depends on the locations inside the room, the acoustic source. When I mentioned to you that this is in the middle of the room, but it is on the floor, you can set Q is equal to 2. Okay? And how about A? A, it depends on whether this is a point source or a live source. If this is a point source, you can set A is equal to 4 pi R square. If this is a live source, you have to set A is equal to 2 pi RL. Okay? It depends on the type of source. Is it clear? Okay, for this one, for the last term is 4 derived by RC. RC, how to calculate RC? RC is equals to A divided by 1 minus alpha m. This is the room constant. Okay, I will write again. Okay, this one is the room constant. It is relevant to reverberations field. RC is equals to A divided by 1 minus alpha m. Okay, so based on these equations, we can make use of this one to find out the reverberations effects, direct effects. Okay, if in these equations we do not need to consider the effects of the direct field, if we do not need to consider the reverberations field, if we assume that all the sound fields can be absorbed, that means no reflections effects. We just need to consider the first term. Okay. For the second case, if we achieve the steady state, we do not need to consider the direct field. Why under steady state effects we do not need to direct field? You may go back to this figure. This one. In this figure, we just consider two components. If under a steady state components, it means that the reverberations effect dominates the effect of the direct field. Correct? Because the longer the distance, the lower the direct field until the total level is almost the same as the reverberations level. So at the steady state mode or steady state level, we just need to consider the reverberations components. I will demonstrate an example to you later on. Okay, for the procedures, number 1 to number 5 here. I want to construct the relationship like this, and when we construct the relationship like this, you can follow the step. When you can consider this one, you can follow back the procedure here. Okay, this one. You can construct this equation. But I could not tell you how to derive following these 5 stages. Okay, this is just for your reference. You have to understand this equation. This is good enough. when you pay attention on this one, reverberations field, I stay a term here, is I is equal to P square over rho C. I stay constant here, 1/4. You may compare the previous one, why we have this one, 1/4. I don't want to go through the details about that because there are alternative ways we can derive this one. You may consider that under the reverberations effect, reflections effects, the energies could be reduced, okay, because we have energy loss. So that's why when we use these equations, we need to incorporate the constant 1/4 into this one. Okay, this is just for your information. So please pay attention. This is the most important equation. Okay. One design criteria why we need to do this one. When we operate a building, okay, we need to check. We need to decide the usage classifications, whether this is a classroom, office room, library, theater. Okay, we have different occupational uses. In that sense, we need to decide the acoustic effects. We use several parameters to define this one. The first one is background noise level. The second one is NC curve. This is the noise criteria curve, and the final one is the reverberations time. Background noise, it is very simple. We just use sound level meters to do measurements to find out the background noise. How to find out the NC curve? What is the usage of this one? There are two types. We call this is one is the NC curve and other one is NR curve. The working principle, they are the same, no difference. One is adopted in the United States and one is adopted in Europe. Okay, the only difference is this one. Okay, the working principle, they are the same. This is the charts for NC curve. You can see that this one is the sound pressure level. This is the frequency. What is the range of this one? This is 1/1 octave, 1/1 octave. Okay, not 1/3 octave. Because 1/1 octave, it means that when we double the distance, we can only increase 1 octave. What is the usage of this one? How to make use of this one? When we have a new area, we use a sound level meter to measure the data across the whole spectrum. And then you can use the measured data to find out that what is the weighting of this room. This is just a single weighting system. There are three basic principles. If I just explain this one, if I just read them all these three conditions to you, you don't know what I'm talking about. Let us go to this page first. We need to check the design criteria, whether it can fulfill the relevant conditions. For example, if we want to design a kitchen, the NC weighting must be equal to 40 to 50. Okay, if we check that the area for a kitchen, it can fulfill this one, this is good enough. If we design an office like this one, but the NC weighting, finally we got that is equals to, let's say 45, it means that we cannot fulfill the recommended guidelines. So you need to install more effective materials inside that area in such a way that we can check again and see whether it can fulfill these recommendations. Okay, how to check this one? Okay, no matter we use the NR or NC curve, they are the same, but only the difference is that one is commonly used in Europe and one is used in the United States. This is NR weighting. Okay, let me show you an example using the first in-class exercise here. Now, given that we have a measured sound spectrum listed in table 1, this is 1/1 octave. Find the corresponding NR weighting for this spectrum using table 2. What is table 2? Table 2 is this one. This is a standard table, standard one. Okay, let's see how to make use of this one. There are three conditions here. The first one, we plot the background spectrum on an NC chart or NR chart. Okay, this is the first one. The second one, we have to find out the highest weighting that can envelop all the data. I will express to you later. And the final step is that you have to express the weighting in terms of a whole number. It means that it should be an integer. Okay, go back to our data here. This is the standard charts, correct? And this is the measured level, the red color figures. Okay, based on table number 1. Based on this one, just listen to me how to find out using this NR curve. First of all, you have to identify which value is higher than the measured level under different frequency values. For example, which one is higher than 40.5? Which one? Okay, with the data for the whole column, which one is higher than this one? Which one? 55, correct? The first one, 55, is higher than 40.5. How about the second one, 41.5 at 62.5 Hz? Which one? 43? Okay, across the whole spectrum, you identify one by one. Okay, 50.5, 57 is larger than this one. 59 is larger than 55.4. Okay, any problem? This is the first step. And then we need to find out the highest weighting that can cover the full spectrum. Which one is the highest weighting now? Okay, you can see that at 2 kHz and at 8 kHz, we have two figures, 68, 68 and 64. They correspond to NR70, okay? Other than 2 kHz and 8 kHz, other than that, all of them must be equal or less than NR60. I repeat again. When you refer to this one, okay, when you go through the spectrums here, only at 2 kHz and 8 kHz, the values can up to NR70. All other frequency values, they are lower than NR60 or equal to NR60, correct? So we just consider these two values at 2 kHz and 8 kHz, okay, because now we are going to find out the highest value. We do not care about those below that value. Okay, now how to calculate this one? Let's go to 2 kHz first. 58.8 should be in the range 57 and 68, correct? 57, it corresponds to NR60, and 68 it corresponds to NR70. So we need to do a simple interpolations. Okay, we just need to do a simple linear interpolations to find out that 58.8, it should be corresponding to 61.6. Okay, any problem about this one? But we still need to consider another figure is 8 kHz. For 8 kHz, the correspondence value is 55. It is in between 54 and 64. So we follow the same procedure. The value for 55 is NR61. NR61. Which one is larger? At 2 kHz, correct? So the highest ratings should be, and cause the full spectrum is NR62, not 61.6, because we need to express it into integer, whole integer, okay? And the highest value at 2 kHz, okay? Once you got the data here, you can compare you can compare this figure, okay, no matter this is NR or NC, this is the recommendation, okay, to see whether they can fulfill this one. If, let's say, if you design a kitchen that cannot fulfill this one, what does it mean? It means that you need to install more optical materials inside the area, such that you can lower down the level and do against the measurement and check again the data, okay? Any problem about how to find out the overall NR weighting? NC weighting is the same. Okay, for this one, 61.6, so that's why we express it in terms of 62. How about 61.2? How about 61.2? We still consider that we round up to 62, round up, not round down, okay? Because we have to find out the exact value that can envelop all the data. Okay, this is the purpose of this one. And this one, and the usage of this figure is to find out whether the background effects that can fulfill our design criteria. Okay, any problem? Another one is that we can use the reverberations time to find out the results, whether it can fulfill the design criteria. You can see that this is a chart to show that if we design different if we have different classifications such as office, building, cinema, or something else, you can make use of this one to decide the effects. T60 is the reverberations time. This is the equation to find out the reverberations time. When you consider this one, what is this? This is A. Okay, this is A, total absorption effects. And so that we can write it as 0.16 times volume divided by A. Okay, V, the capital letter V is volume, the volumes of a room. The definition is that reverberations time of a room is the time when we just turn off the sound source, and it can decrease it by 60 dB. This is the time. This is the time effects. This is the reverberations time effects. And we can make use of these parameters to find out to achieve the size of a room. It is not dependent on the positions in a room, and it depends on the dimensions, because when you refer to this this equation, it is relevant to volume. Okay. Okay. Let me show you how to measure this one. Okay, and also why it is so important when we need to have a correct design for an interior room acoustics, because we can listen to this one. This is the reverberations time, and the reverberations time is 5 seconds. Under these conditions, you cannot clearly listen what this lady said about. Okay, you cannot hear the message, correct? Now, when we lower down the reverberations time to 3 seconds, it is better now. Okay, but still not very clear. It is better now. This one is the best amongst all other previous cases. But if we further reduce the reverberations time, it doesn't mean that we can achieve the better results. So that we need to adjust the optimum reverberations time effects, because it is relevant to our intelligibility. Okay, whether it is clear or not, when we design our musical theater, okay, this is very important. Okay, if we achieve a higher reverberations effects, we cannot hear clearly. Okay, and how to measure the reverberation time? Here, this gentleman mentions that they use the pen noise. Okay, for the pen noise, in terms of the pen noise, you can refer to the first lecture logs. Okay, we use the color of noise to represent different behaviors or the signal effects. Okay, referring to this column, you can find out the frequency. When we measure this reverberations time, they are different. Okay, this is the time. And the definition is that when we turn off the source, it can be decreased by 60 dB. This is the time for reverberations effects. Now, this is an example to show that how we can find out the acoustic power level of the motor. This is an electric motor that can be produced by a steady state reverberation sound pressure level of 75 dB in a room, 3 meters times 6 meters times 15 meters. The measured reverberation time of the room is 2 seconds. What is the acoustic power level of the motor? Because of the time limit, let me explain to you. We can ignore the direct field effect because this I state here is steady state reverberation sound pressure. So that sometimes direct field, because it could be decreased when we increase the distance, we can ignore this one. Okay, how to find out this one? Based on the information provided in the questions, we just know that the reverberation time is 2 seconds. So when you recall this one, when you recall this equation, when you refer to this equation, this is relevant to V and also the surface area, correct? And how about, do you know the surface, the individual surface area? We don't know it, okay, because it's just mentioned, we just have this one, we know this one because we have 3 meters times 6 meters times 15 meters. So when you refer to this equation, because the volume is 270 meter cube and T60, the reverberation time is 2 seconds, 2 seconds. And how about this one? When you refer to this one, this is equal to A, correct? When we can set up A, actually the FH value alpha. Here, this is the FH absorption coefficient is equal to A divided by the total surface area, correct? So when you refer to this one, the total surface area is 306 meters square, and so that when you rearrange some terms, you can find out the FH sound absorption coefficient. In this case, is 0.07. Okay, when you refer to this figure, this is highly reflective or highly absorptive inside this room. Highly reflective, okay, because it is closer to 0. Okay. Okay, alpha with a bar here at the top is the average absorption coefficient. So that in this case is equal to 0.06. Now we have to find out the acoustic power level, not this one. What other equations we can make use of? We can consider this equation. Okay, these equations can help you to find out the overall sound pressure level and the overall sound power level based on this one. The first term here, Q divided by A, this one is direct field. And the second one is the reverberation field. As indicated by the questions, for the direct field, we do not need to consider this one so that we can ignore this one. Okay, we recall this equation. For the first one, for the direct field, because we don't need to consider this one, so we set it is equal to 0. We just consider the second term. For the second term, this is the room constant. We can consider into we can recall this equation to find out that RC is equal to 23. When RC is equal to 23, please pay attention. We are looking for the acoustic power, not acoustic pressure. The acoustic pressure is given is equal to 35, so that the acoustic power is equal to 82.6 dB. Okay, this one is. It makes sense because the sound power must be higher than the sound pressure level. The longer the distance, and even affected by the surrounding area, the sound pressures could be decreased. Okay, any problem? Okay, reverberation chamber. Reverberation chamber methods. What is that? This is used to test the effects, the absorption coefficients on a material. Okay, the absorption coefficients. How to make use of this one to test the absorption coefficients? This is a standard guideline. We do not go over the details about that. I just highlight the general information about that. Inside this room, this should be highly reflective. Okay, the walls, ceiling, and floor, they should be made of smooth, and sound reflective materials. And the test should follow this ISO standard. And the normal size should be is suggested to be 200 meter cube. The test samples should be 10 meters to 12 meters square. This is the standard setup. We put the testing material on the floor, and then we can check the absorption coefficients of that material. The working principle is so simple. We just make use of the reverberation time. The procedures are listed here. Before we put this material inside this testing lab, we measure the reverberation time. After that, we put this material inside the lab, and we measure again the reverberation time. Because now we have one more materials here, the reverberation time must be changed. Correct? When we compare these two parameters, we are able to find the absorption coefficients. These are the procedures. And what are the equations we can find out this one? This is the equation. Alpha is the material absorption coefficients. V is the volume of this testing lab. S is the surface area. C is the speed of sound. And how about T1 and T2? T2 is the reverberation time with the presence of this testing sample. And T1 is without this testing sample. We can compare this one. I listed here is just for your information how we can make use of the equations of reverberation time to derive this equation. Okay, this equation is that we compare two scenarios, one without a testing sample and one with a testing sample. We consider from this equation, and then if we put a new material inside the testing lab, so it means that we have one more term, the absorption coefficients, due to this testing material. So when you compare the difference between these two, without and with testing materials, we can construct this equation. Okay, and so 55.3, actually it is equal to 0.16, because when you check it by yourself, when you use 55.3 divided by 344, it is equal to 0.16. And what are the advantages of using these testing methods? Because if we have a standard laboratory, we can repeat the standard results, okay, and we can reproduce the effects. The problem is that there is an edge effect that could affect the weighted measure results. What is the edge effects? Similar to this one, we need to put our testing material on the floor because this material has some thicknesses, okay? At the edge of these materials, when sound fields, okay, hitting on these edge materials, it could have reflections effects because the presence of the reflections, so that it may affect the final result. But this is still a standard approach. So although this is a shortcoming, we still need to use this one for our testing. For the types of sound absorption materials, we may have some, we can classify into three general types. The first one is the porous materials, the second is the flexible material, and the final one is cavity. We make use of these three materials to do absorption effects inside our buildings, no matter in the ductworks or in our walls. Okay, even you know that in the air ventilation ducts, we need to install some materials to enclose the ventilation ducts, because under the working effects of this ventilation duct, it could generate noise effects. For the porous materials, this is one of the porous materials. We call this one is rockwood. Rockwood is a kind of mineral material. The mechanism is that when sound fields add on this one, because there are many micro scales size, so that it could generate the frictions in between the acoustic wave to change from the mechanical wave to other energy forms. And it is more useful. It is more useful for high frequency. For high frequency, when you refer to this one, this is the absorption coefficients, and this is the frequency range. Low frequency, you can see that the absorption coefficients is much lower than that for high frequency. Okay, so that it means that for porous materials, it is more suitable for mediums to high frequencies. For low frequencies, it is not so effective. And when we use the raw materials, some materials, they are fire retardant material, but when you use for a long time, we need to replace it. Okay. The second one is the flexible materials. We may make use of the sound blocking membrane or the acoustic rubber as the flexible materials. The durations of this one is much longer than the porous materials, but after a period of time, we still need to replace it. It is more suitable for mediums to low frequency noise. You can see that this is a typical effect with the flexible material. It is more suitable for the medium effect. The absorption coefficients is can up to 1, but for high frequency, it is down to below 0.52. And the other one is the cavity materials. When you go to the lecture theaters in our campus, you can see this one. You can see this design. Okay, this is what we call the perforated floor, perforated walls. There are many small pores here, but when you compare the scale of this one, this is much larger than this one. Okay, this is a much smaller scale. Okay, for this one, the working principle is very simple. We still need to make use of the friction effect. It is similar to this one. Air is elastic material. Okay. This is a bottom, and this empty bottom, when sound waves pass through this one, it could mix the acoustic wave into other energies. And you don't need to memorize this equation. This is just for your reference. When we consider the effects like an empty bottom here, when we want to find out the resonance frequency, you can consider that by taking the area, volume, and also the length of this one to calculate the resonance frequency. But this is just for your reference. Please do not memorize this equation. And for the cavity materials, we consider it is more effective for medium frequency, not for low frequency. Okay, for the sound transmission loss, it is about that, how to prevent the sound effects from one area to another one. Okay, let us take another break first. We will go through the rest of them in the third part. Okay, we go to the last part. We almost took about more than 1 hour to explain how to calculate the absorption effects. In the second part, I also introduced a term to use the sound blocking. I want to show you a very short video about what is the difference between the sound absorption and sound blocking. So when you compare these two terms, acoustic absorptions, the target is to make us to speak clearly or to hear clearly to enhance the intelligibility. For installations or what we call the sound blocking, it refers that we don't want to have some sound effects that can transfer from one area to another area. Okay, but how to test the sound transmission effects? We may refer to this one. This is the sound transmission loss. Difference to this one, we define this is the amount of sounds that can be isolated by a material, and the transmission loss or the partitions is an intrinsic properties that is independent of the acoustic property of the room. There is a statement here. Transmission loss is not the sound pressure level difference between the source room and the receiver room. I will explain to you why I say a statement here in red color. Sound transmission coefficients, when we are talking about coefficients, all of them, they do not have units, okay? And similar to the sound absorption coefficients, this is a non-unit coefficient. We use power to represent the transmission coefficients. In terms of the transmission loss, we can write it in this form, okay? Transmission loss, when we write it into dB, we can use this equation. And how about this one? How to calculate the sound transmission loss? Why we have this equation? Let's say we just have a wall. Sorry. If we just have a wall, okay, we have a single value for its sound transmission loss, correct? When sound waves pass through this one. But now, if on this wall we have a door, we have two components, correct? In this case, we need to find out the average sound transmission loss. We need to follow these equations. Okay, let's say we have two components, one for the door and one for the wall. So we can calculate the area of the wall and the area of the door, and they have their corresponding transmission loss coefficients. And how about this one? A is the total area. Okay, let me explain more about this one. Okay, this is a wall, and this is a door. So AW is the area for the wall, and AD is the area for the door. What is the total area? The total area is equal to AW plus AD, correct? Okay, please bear in mind that this is the wall area. Okay, for each of them, AD, the corresponding transmission loss is tau W, and for the door is tau D. So you can make use of these equations to find out the FH value. This is the FH value. If we just have a single element, just a wall, we do not need to make use of this one. If more than one components, we need to consider this one. Any problem? Similar to this one, if we want to find out the FH transmission loss for this area, okay, we have a wall like this. Okay, we have a wall and two doors. Okay, on this side we have a wall and two doors. So that in total we have three components. To find out the overall or the FH transmission coefficients, we need to follow this simple equation. Now, in our lab test, if we want to test the material, the transmission loss of the material, we could use two-room systems. One is called the source room. We have a loudspeaker here, and the other one is the receiver room. We have a microphone here. This is the test sample, like this one. When we generate the loudspeaker, when we turn on the loudspeaker to generate sound fields, we can measure the sound pressure level here to find out the transmission loss of this test sample. We could make use of these equations to identify the transmission loss of this test sample, but when you read carefully on these equations, there are three terms on the right-hand side. L1 is the sound pressure level in the source room. Okay, in the source room, we still install a microphone here. L2, what is L2? L2 is the sound pressure level in the receiver room. That means on this side. And how about this one? 10 naught S divided by A2. S is the area of the test sample. And what is A2? A2 is the sound absorption area in the receiver room. Okay, sound absorptions of the receiver room, this part. Okay. There are different approaches to derive these equations, but one simple expression is like this. Okay, let us rewrite into this form. L2 is the sound pressure level at room 2, correct? What is this one? We have an acoustic source inside the source room. When it generates the sound fields, some of the sound fields could be blocked by this test sample, and some of the sound fields could be absorbed by inside this receiver room, so that the remaining parts should be measured by this speaker, correct? This microphone. So when you rearrange this one, L2 is sound pressure level at room 2, and on the other side is sound pressure level at room 1 minus transmission loss and minus room absorptions. You can find out the results. Okay. This is the room absorptions for the receiver room. Okay, receiver room. So when you rearrange this one, it becomes L1 minus L2. When you change this one to this part and L2 to this one, you can get the same equations, correct? But you may ask a question. But you may ask a question is that on the for this third component, this is minus room absorptions, minus the effects for room absorptions. But why this is positive? Okay, I stay here is negative. Why I present in this equation is positive? This is correct because when you refer to this term, we want to take away from this one, the room absorptions. In this part, you can write it as A over 2, not minus, like this. But when you change the upper part to the lower part, when you reverse it, this could be changed to positive side. Okay, this is the easier ways to understand that how we can construct these equations. So when you go back, to this page, there is a statement here. Transmission loss is not the sum pressure level difference between the source room and the receiver room because we still have the last components. This one. Okay. Okay, for different building elements, in terms of the transmission loss, these are common materials. For example, the breadboards, the transmission loss can be up to 55. It means that when sound fields pass through this one, 55 dB can be isolated. Okay, the amounts of sound energies of 55 dB can be isolated. This is just for your reference. Okay, find the transmission loss of the material that has sound transmission coefficients. The first one, there are three small questions. The first one is that the coefficients. One is 6 times 10 power to minus 4. The second one is we want to find out the transmission loss, the transmission coefficients for a concrete block, 40 dB. And the third one is that an open window has a transmission loss of 0 dB. Find the sound transmission coefficient. Why we have an open window? The transmission loss is 0 dB. Because when you open a window, none of the energies can be blocked. All the sound fields can pass through this one. So that's why the transmission loss or openable window is 0 dB. Okay. Okay, because this is just short questions, let's take a look. We just recall the first equation like this to find out the transmission loss. Because in the first questions, the transmission coefficients is equal to 6 times 10 power to minus 4. So that's in this case, the transmission loss is 32 dB. For the second one, transmission loss is 40 dB, so that's its correspondence values for the transmission coefficients is 0.0001. And the last one, because the transmission loss is equal to 0, it means that tau is equal to 1. All incident sound waves can be transmitted. If the transmission coefficient is equal to 0, it means that all sound fields could be blocked. Okay, this is just for a single element. Okay, if the case like I explained to you before is that we have more than one components, you need to find out the overall or the average coefficients first. Okay, this one is to another standard, another standardized approach. We want to find out the transmission loss of the material. We have two standards, the ISO standard and ASTM standard. ISO standard we refers to the European standard, and ASTM we refers to the United States standards. Okay, when we refer to ISO standard, the number weight, and we call this one is the weighted sound reduction index. When we refer to the United States US-based approach, we call this is the sound transmission class, and we refer to ASTM E413. What is the difference between them? We just have two different systems, but the working principle is still the same, similar to NC and NR weighting. We use this ones to determine or identify the transmission loss behavior of the material. How to find out this one? Okay, let's jump to this page. The highest the sound transmissions class value, the highest the overall sound reductions. And this is still a single number weighting. Still remember that NCNR weighting, this is single weighting. We just have a single value to represent the behavior or the background noise level inside a room. And this is still the same. Okay, let me introduce to you. Please go to this one. When you refer to STC, sound transmissions class, or the weighted reductions index, they're the same. Please bear in mind these two conditions. The first one is the maximum deficiencies should not be more than 8 dB, and the total deficiencies across the whole spectrum should not be more than 32 dB. Okay, what are the usages of these two conditions? Because after that, we can identify the STC weighting. We can find out that whether this is a good performance or not. If let's say if the STC weighting is 25, the normal speech understandable, but the noise control level is at a poor level. And because I told you that this is just a single value, we just need to identify with the data at 500 Hz only, 500 Hz. In this figure, the upper part is the weighted reductions index, and the lower part is the STC weighting. When you compare the first one and the second table, the correspondence levels, they are the same. For example, at 125 Hz, the reference contour is minus 16 dB. Okay, please pay attention. These are not absolute values. They are just reference values only. Okay. When we check the weightings of the material, we follow these two conditions. And let me show you an example. Okay, this is the charts across the whole spectrum. This is 1/3 octave, not 1 octave, and this is the sound reduction index. The red one is the test result of the material, and then we plot this test results on this figure. And the yellow one and the black one, they one is for the weighted reduction index, and the other one is for STC. But both of them they are the same. You can see that they are overlapped with each other. We can move this standard curve up and down, okay, until it can fulfill two conditions. The first condition is that each frequency band cannot be more than 8 dB. This is the first condition, and the second condition is that the overall deficiencies cannot be more than 32 dB. Okay, let me show you an example here. How to read the data here. The purple one is the standard curve. Okay, this one. You can move up and down. Okay. Okay, and the black one are the measured results. Okay, how we can adjust the standard curve in order to find out the single number weighting STC. How to read this one? Okay, for example, when you plot this one, you can we have to compare each frequency band one by one. For example, at 125 hertz, the value between the transmission loss and the standard results is HdB. You can count here, okay, the difference. When you consider 125 hertz here, you have to check the value here cannot be more than HdB. The maximum value is HdB. Okay, you have to check one by one across the whole spectrum. And then when you list out all the deficiency value, deficiency means that the difference between the measured data and the standard curve. Okay, you cannot move up and down for this measured data. You can only move up and down for this standard curve. Okay, to check the value. In this case, the first one at 125 hertz, the difference is HdB. This is the maximum value. We cannot more than that. The second one, in this case, is the difference is 6 dB until you can locate all the values here. The total deficiencies. Now, when you sum up all the data here, is 32. We can fulfill the second conditions. But when you look carefully at this table, why some of them we do not need to have we do not need to calculate the deficiency. For example, at 500 hertz up to 2K hertz, we do not present any data here. Correct? Why? Okay, please take a look on this figure. From 500 hertz up to 2K hertz, all the data here they are above the standard curve. Correct? When you just compare this two. There is a statement here. No credit is given for transmission loss data above the contour. It means that for those data above the contour line, we do not care about that. We do not need to calculate the deficiency. We only need to calculate the data for those data below the standard curve. Okay, but you cannot tell me that I need to adjust the standard curve or below the standard curve. It doesn't make sense. Okay, in this way we cannot calculate the results. Okay, once you fulfill the first conditions, each frequency band should not be more than HdB, and the total deficiencies should not be more than 32 dB. Now you can read the data at 500 hertz. What is the data? At 500 hertz in this case is 57. Okay, when you read this one at 500 hertz, you need to refer to this standard curve or this measured data. Which one? You need to pick up. You can go back to this one. When we fulfill all these two conditions, okay, the data we read it from the standard curve, not the measured data. Okay, this example shows that RW is equal to 47. We call this is the RW47. And in this case, at 500 hertz, you locate the data here. Okay, this is the standard curve. The correspondence value here is 57. So that we call this one, this material has the STC value of 57. We just read the data at 500 hertz. Why we need to select this one, not other frequencies? Because we need to have a standard. Okay, you cannot pick up the value at 1K hertz. I pick up the value at 500 hertz. We cannot compare the data. So we set at the beginning. We just read the data at 500 hertz only. Okay. When you go through carefully about this one, at 500 hertz, the reference contour is 0 dB. If I told you that, now I can find out the STC value is equals to 57. 57, it means that at 500 hertz, you can identify the value is 57. How about at 400 hertz? At 400 hertz, the value is 56. Okay. At 350 hertz, it means that it is equal to 54. Okay. This is just reference contour, not exact values. So that's why I told you that we can move up and down in such a way that you can locate an optimum result. When you our second experiment, we will make use of those ones to find out the single weighting values of the material. If we do it manually, okay, maybe we have 1 to 2 points difference, okay, but this is just a minor difference. Normally, we can make use of the computer software to do computations for that. But behind the working principle, this is the scenario, okay. Any problem about how to read the data for STC in this case? We do not need to set the total deficiency that is equal to 32. Okay, if it can be less than 32, we can stop our calculations and read the data at 500 hertz to find out the single weighting value. Okay, there are numbers of factors that could affect the transmission loss. I could not go through details one by one because these are just a general knowledge about that. When we increase the transmission loss, it is expected that we increase the mass of a wall. When we increase the thickness or the dimensions of a wall, it can increase the transmission loss. Okay, and the heavier the structural elements, emit these materials less vibration, so that's why you can reduce the transmission effects. And I also told you before that when we use a double panel, this is a common approach. We would use this one, but there are some general design features. For example, we want to make the air gap as large as possible, and we also install some absorption materials inside this one, and we have to make sure that there is no any interconnections between these two panels. In addition, we want to make the mass or the thickness of these two panels, they are slightly different because we want to avoid the presence of resonance effects. Okay, silencer. Silencers, this is engineering devices. We can make use of this one to reduce the noise level. Sometimes when we want to allow the passage or airflow, but we want to control the noise effects. For example, we want to build up an industrial area. We may make use of the silencers. There are 3 terms here: insertion loss, transmission loss, and the noise reductions. I will explain to you one by one. This is a typical examples. We use it as silencers. When you refer to these figures, you can see that there are some absorbing materials. You can allow airflow passing through this device. Because of the presence of these sound absorbing materials, you can absorb sound effects. The second one is okay, let me explain to you what is insertion loss first. Insertion loss is the difference in some levels measured at a given location before and after a barrier or silencer is installed. What does it mean? For example, we have a source here, okay? At the receiver, we use the sound level meters to measure the data SPL1, okay? Now, when we install a barrier and we measure again at the same position, it must be at the same position out. We measure SPL2. Insertion loss is the difference between these two values, okay? It means that SPL1 minus SPL2. Insertion loss, we reverse that it must be at the same positions before and after the installations of a barrier or an enclosure, okay? Another example is like this. If we want to do a cover, this is a source. We measure here, this is R. So at the beginning, we measure the sound pressure level, SPL1. Now we use a cover to enclose this sound source, but we measure again at these positions, the same positions. We got SPL2. Insertion loss is still the same, SPL1 minus SPL2, okay? We are talking about at the same positions. This is what we call the insertion loss. So that no matter this is a dynamic insertion loss or the static insertion loss, we are talking about that we are measuring at the same positions, okay, not at different positions. If we measure at different positions, this is not insertion loss. And we usually use the dissipative silencers in our air ventilation systems. Chiller here. Chiller means that this is the heat exchange device, okay, to exchange heat effects. Because that there is a strong airflow from interior areas to exterior areas for heat exchange. So to reduce the environmental noise effects, we may make use of the dissipative silencer. And we have another one is the reactive silencers. Reactive silencers, it is the structure of the reactive silencers. We have different chambers. Inside this one, because of the combinations of different chambers, it can induce reflection effects inside this internal structure. So that's why it can reduce the noise effects. For the reactive silencers, this is an equation we can make use of this one to calculate the transmission loss. You do not need to memorize this equation, okay, just for reference. In this equation, you can take a look on that. M is the cross-sectional area ratios. That means we compare the ratios between S1 and S2. With different combinations of these area ratios, we can achieve the reduction effects. And when you take a look on this one, this is the power gun, and this is what we call the reactive silencer in motorbikes, okay? And the internal structures of this device is like this, okay, with different components, with different chambers. Okay, for the enclosure, it is very simple. We just use a cover to enclose an acoustic source. Normally, we use this one in construction areas or in industrial areas. When we refer to this, to design an appropriate enclosure, we need to consider that we want to make it with an openings because we need to make sure that there is ventilations or we can access inside to do maintenance. Inside the enclosures, we need to have an internal absorption effects, and we want to make the areas of the enclosure as small as possible. And lastly, we still need to consider that the materials made use for this enclosure in such a way that we want to isolate as much as sound energy as we can. And finally, in addition to these four factors, the first one, openings, internal absorption, area of enclosure, and transmission loss. All of them, they are just for the control of airborne noise effects. Airborne noise. For the final one, vibrations, isolations, this is for structural borne noise control. Okay, so that's when you design an enclosure, we need to consider both of them because normally we use the enclosures to cover machines, okay, working machines. All these four factors, they are just used for airborne noise control. For the last one, this is for structural borne noise control. We will take about 3 lessons to go through how to design an appropriate vibrations isolation system. And the term here, isolations, what does it mean? It means that we want to minimize the force, the vibrations force that can be transmitted to the structure, okay? If we can reduce the amount of force that can be transmitted to the structure, supporting structure, it means that we can control the structural borne noise. Okay, I explained this one to you before. When we are talking about the insertion loss, we always assume that this is at the same position, okay? We measure at the same position at the receiver. And this equations is to help us to calculate the insertion loss on the enclosure panel. I don't want to derive how to find out this one. The first term on the right left-hand side is insertion loss, and on the other side is transmission loss, and this is the room constant inside the enclosure, And S is the surface area of the panel. And finally, this is the noise reductions. Please pay attention. Noise reduction is different from insertion loss. When you refer to the definitions, it just compares the difference between the sound levels between the source and the receiver. But sometimes when you refer to some reference books, they could just write noise reductions by absorptions. Let's say when we measure inside a room, okay, before installations of absorptive material and after installations of absorptive materials, they also call this one is the noise reductions effects. Okay, but even we are at the same positions, we measure at the same positions. They also call this is the noise reductions effects. Okay, I want to remind this one. When you refer to this equation, NR is equals to this part, the total absorptions. You may regard this as the final conditions. Final conditions, it means that when we apply the new absorptive materials, and the initial conditions, it means that before the installations of absorptive materials, okay, they can make use of these equations. But this is a simple form. This is a simple form. This is a simple form for this one because do you still remember that we use the RC? RC is the room constants to find out this one. Okay, in this case, they just assume that alpha m is very small. Okay, when alpha m is very small, it means that the low part is almost equal to 1. So that's why the room constants is approximately equals to A. Okay, when you do calculations, I suggest that you go to this equation rather than you use this simple form. Okay, because this is just a particular case, we assume that the absorption coefficient is very small. If the absorption coefficient is not that small, this one may have a calculations error. Okay. So the design of enclosures, I already told you before that this is a typical example here. Normally we use an enclosures to cover some industrial machines. To cater for the noise control for machines, there are two aspects. One is for airborne noise and the other one is for structural borne noise. The 4 points here, the first one is use of steel material, provided inert surface with sound absorption materials, mount silencers, and supply the enclosure with inspection patch. In general, they're used for airborne noise effects. But when you refer to this figure, there is a term here. We could install some anti-vibrations pad here. The purpose of using the anti-vibrations pad is to reduce the force that can be generated from these pumping machines to be transmitted through the connected structures to outside. This is the difficult part for noise control, okay? Because we have, when we have structural connections, it is difficult to control where is the source and where the sound effect, the energies could go. But we could further consider this one later on in our study. Okay, we may stop here for topic number 3. If you have any problems about the explanations tonight, you may ask me by emails or ask me in the later lessons. Please bear in mind that we have compulsory lab sessions on the next 5 days. You must attend these lab sessions. Okay. Okay. Thank you.